Hello student, welcome to your chemistry lab. Today I am discussing electrochemistry part 3, that is electrochemical series and its application and nonce equation related numericals. It is important for JEE and NEET and also for board. So read very carefully. So now watching the whiteboard. Electrochemical series or electropotential series. Electrochemical series is the arrangement of various electrodes of elements in the increasing order of their standard reduction potential or decreasing order of their standard oxidation potential. Important characteristic of electrochemical series. Point A. In the electrochemical series, the half cell reaction or electrode reaction are written as the reduction reaction. Example, reduction reaction at Zn2 positive Zn electrode is Zn2 positive plus 2 electron gives Zn. Here Zn2 positive and Zn are the oxidized and reduced form respectively. Point B. Standard electrode potential of hydrogen is taken as a 0. Elements placed above hydrogen have negative standard electrode potential and those below hydrogen have positive standard electrode potential. Point C. On moving bottom to top, the standard reduction potential of the electrode gradually increases. Higher standard reduction potential of an electrode, greater is the tendency of the reaction occurring as a reduction reaction. On the other hand, the smaller standard reduction potential of an electrode, the greater tendency of the electrode reaction to occur as an oxidation reaction. Point D. The smaller the standard reduction potential of an electrode, the greater the tendency of its oxidized form to be reduced. This means that oxidized form will act as a stronger oxidant and the reduced form will act as a weaker reductant. The smaller the standard reduction potential of an electrode, the greater the tendency of its reduced form to be oxidized. So the reduced form is a stronger reductant and the oxidized form is a weaker oxidant. Example, Li positive Li electrode lies at the top of the electrochemical series. Hence, its standard reduction potential is minimum. Therefore, in aqueous solution, the tendency of Li to be oxidized, that is tendency to function as a reductant, is maximum, and the tendency of Li positive to be reduced, that is the tendency to act as an oxidant, is minimum. On the other hand, half F2 F minus electrode is at the bottom of the electrochemical series. Hence, its standard reduction potential is maximum. Therefore, in aqueous solution, F2 has the maximum tendency to be reduced or act as an oxidant. F minus has the minimum tendency to be oxidized or to function as a reductant. Utility of electrochemical series. The electrochemical series given an idea about the relative chemical reactivity of the element. Point A. Displacement of hydrogen from dilute acid solution. Displacement of hydrogen from dilute acid solution is a reduction reaction. 2H plus 2 electron gives H2 gas. The standard reduction potential of hydrogen is 0. Hence, metal having negative standard reduction potential, that is metal occupying higher position, is the electrochemical series than hydrogen. Reduce H plus ion from dilute acid solution to produced hydrogen gas. Example, in the electrochemical series, zinc lies above on the hydrogen and has a standard reduction potential is 0.76 volt. Hence, Zn reduced H plus ion of dilute acid solution to produce hydrogen gas. That is Zn plus 2HCl gives ZnCl2 plus H2 gas. On the other hand, Cu lies below the hydrogen in the electrochemical series with standard electrode potential is 0.34 volt. Hence, it cannot reduce H plus ion of dilute acid solution to form hydrogen. That is Cu2 positive plus 2HCl gives CuCl2 plus H2. This reaction does not perform. Point B. Production of hydrogen from water. Metal higher up the electrochemical series reacts with water produced hydrogen. The smaller standard electrode potential of a metal, the more likely it will react with water. For example, sodium react with cold water to form hydrogen, but magnesium and aluminium react with boiling water. This is the reaction 2Na plus 2H2O at room temperature gives 2NaOH plus H2. Here reduction potential of sodium equals to minus 2.72 volt. Magnesium plus 2H2O at 100 degree centigrade gives magnesium hydroxide plus H2 gas. Here reduction potential of magnesium equals to minus 2.36 volt, and also aluminium, that is 2Al plus 6H2O at 100 degree centigrade gives 2AlOH whole 3 plus H2 gas. Here reduction potential of aluminium equals to minus 1.86 volt. Point C. Displacement of metal from its salt. A metal having higher position in the electrochemical series can displace any other metal lower in the series from solution. The standard reduction potential of the metal towards the bottom of the series are larger, so the ions of this metal are easily reduced by the metal higher up in the series. Example: Fe lies above Cu in the electrochemical series. When Fe is added to a solution of Cu2 positive ions, it reduces Cu2 positive to Cu, which precipitate in the solution. That is, Fe plus Cu2SO4 gives FeSO4 plus Cu. Here reduction potential value of Fe is minus 0.44 volt and reduction potential value of copper equals to plus 0.34 volt. Point D. Displacement of metal from its oxide. A metal higher up in the electrochemical series has a small standard reduction potential and therefore exhibits as a strong reducing property. Such a metal can reduce the metal ion of the oxide of metal lower in the series. This is when happen the reduction of Fe2O3 by aluminium in thermal process. Aluminium being higher up in the electrochemical series and reduced Fe2O3 to Fe. Reaction is Fe2O3 plus 2Al gives 2Fe plus Al2O3. Point E. Reactivity of metal and their occurrence in nature. Alkali metals, as for example lithium, sodium, potassium, and alkaline earth metal, as for example magnesium, calcium, are higher up in the electrochemical series and hence they show high tendency to lose electron. This is why this metal possess high chemical reactivity and they are not available in free state in nature. On the other hand, metal like Ag, Cu, Au, etc., ranking lower in the electrochemical series, are much less reactive, so they are available in free state. Point F. Extraction of metal by reduction. Since alkali and alkaline earth metal occupy relatively higher position in the electrochemical series, they behave as a strong reducing agent. This means that their oxidized form are very difficult to reduce. This is why this metal cannot be extracted from their compound by reduction, even with the help of a very good reducing agent, as for example carbon, hydrogen. On the other hand, the metal occupying a relatively lower position in the electrochemical series, as for example Fe, zinc, can be extracted from their compound by carbon reduction. Point G. Determination of electromotive force of a cell. In a galvanic cell, the electrode with larger standard reduction potential serve as a cathode and one with a smaller reduction potential serve as a anode. If the electrode potential of the two electrodes are known, the electromotive force of the cell can be determined by using the relation standard electromotive force of the cell equals to standard electrode potential of cathode minus standard electrode potential of anode. EMF measurements application. EMF measurement have wide applications such as determination of pH, KSP, del H and del S, that is pH, solubility product, enthalpy change and entropy change. Point 1. Determination of thermodynamic data. Del G can be determined as del G equals to minus NF E cell. Using Gibbs-Helmholtz equation, temperature coefficient of the cell can be determined. Del G equals to del H plus T d del G by dt at constant P. Since del G equals to minus NF E cell and putting the value of del G, that is minus NF E cell, in equation 1, that is minus NF E cell equals to del H minus NFT d E cell dt at constant P. So d E cell by dt at constant P equals to del H plus NF E cell by NFT. Next, d A cell by dt at constant P equals to del H by NFT plus E cell by T. d E cell by dt is called temperature coefficient of EMF of the cell. Next, enthalpy change can be determined, that is del H equals to minus NF E cell plus NFT d E cell by dt at constant P. So minus NF E cell plus T d E cell by dt at constant P, and entropy change can be determined del G equals to del H minus T del S. Compare with it equation 1. So del S equals to d del G by dt at constant P equals to minus dt minus NF E cell at constant P equals to minus NF d E cell by dt at constant P. Point 2. Determination of equilibrium constant. We know that del G equals to del G 0 plus 2.303 RT log Q. At equilibrium, del G equals to 0 and Q equals to equilibrium constant, that is Keq, that is reaction quotient equals to equilibrium constant. Therefore, del G 0 equals to minus 2.303 RT log Keq. So putting the value of del G 0, that is minus NF E0 cell equals to minus 2.303 RT log Keq at 298 Kelvin, that is standard temperature. The value of 2.303 RT by F equals to 0.0591 volt. So E cell equals to 0.0591 by N log Keq. Point 3. Determination of solubility and solubility product. In half cell contain electrolyte in a saturated solution as given, that is Ag plus salt bridge, Ag plus saturated Agx aqueous Ag. Then at anode, Ag solid gives Ag plus electron. At cathode, Agx solid plus electron gives Ag plus aqueous plus X minus aqueous. So overall reaction is Agx solid gives Ag aqueous plus X minus aqueous. Hence the solubility product can be evaluated E0 cell equals to E0 Ag plus E0 X minus Agx. So E0 cell equals to 0.059 by N log Ksp. So log Ksp equals to NF E0 cell by 0.0591. Point 4. Determination of a pH of a solution. Using a suitable reference half cell, pH of the unknown solution can be determined. This is the cell PtH2, H plus pH equals to X, salt bridge Cl minus 1 molar, Hg 2Cl2, Hg. Left hand side half cell H2 gas gives 2H plus 2 electron, that is E0 oxidation equals to 0. Right hand side half cell Hg2Cl2 solid plus 2 electron gives 2Hg liquid plus 2Cl negative. The reduction potential value equals to 0.2676 volt. So overall reaction H2 plus Hg2Cl2 gives 2H plus 2Hg plus 2Cl negative, that is E0 cell equals to 0.2676 volt. E cell equals to E0 cell minus 0.0591 by 2 log H plus square Cl minus square by 1. So E0 cell equals to 0.0591 by 2 into 2 log H plus, here concentration of Cl minus equals to 1. So E cell equals to E0 cell plus 0.0591 pH. Therefore, pH equals to E cell minus E0 cell by 0.0591. Numericals. First numerical. Calculate the reduction potential at pH equals to 14 for the Cu2 positive Cu couples. Ksp of copper hydroxide, that is CuOH whole 2, equals to 1.0 into 10 to the power minus 19. E0 of Cu2 positive Cu equals to 0.34 volt. Answer. Here pH equals to 14. So pOH equals to 0. We know that pH plus pOH equals to 14. So here pH equals to 14. So pOH equals to 0. So concentration of OH minus equals to 1 molar. We know that CuOH whole 2 gives Cu2 positive plus 2OH negative. Therefore Cu2 positive into OH negative square equals to Ksp, that is 1 into 10 to the power minus 19. And this equation Cu2 positive plus 2 electron gives Cu. Here Nernst equation equals to ECU2 positive equals to E0 Cu2 positive Cu minus 0.0591 by 2 log 1 by concentration of Cu2 positive. Putting the value of all, so E0 Cu2 positive Cu equals to 0.34 minus 0.059 by 2 log 10 to the power 19, and all value calculated, it gives 0.22 volt. Question number 2. If the reduction potential of the following half cell at 25 degree centigrade V minus 0.3 volt, then determine the pH of the H2SO4 solution in the half cell. Here half cell equals to Pt H2 1 atm H2SO4. 2H plus 2 electrons gives H2. According to Nernst equation, E cell equals to E0 cell minus 0.0591 by 2. Here number of electron change equals to 2, so N equals to 2 log P H2 by concentration of H plus square. Putting the value, E cell equals to minus 0.3, E0 cell for hydrogen equals to 0, and minus 0.059 by 2 log 1 by concentration of H plus square. So log concentration of H plus square equals to minus 10.15, then 2 log H plus equals to minus 10.15, so log H plus equals to minus 5.075, so minus log H plus equals to 5.075, so pH equals to 5.075. Question number 3. Determine the EMF of a decimolar Daniell cell at 25 degree centigrade. Given E0 Zn2 positive Zn equals to minus 0.76 volt, E0 Cu2 positive Cu equals to plus 0.3 volt. So answer equals to anode reaction, that is Zn gives Zn2 positive plus 2 electron, cathode reaction Cu2 positive plus 2 electron gives Cu. We know that higher value of reduction potential is reduction and lower value of the reduction potential is oxidation reaction. So here Zn have minus 0.76 volt, that is the lower value, so reaction performed at anode, and copper have plus 0.34 volt, so higher value reduction occur at cathode. So overall cell reaction equals to Zn plus Cu2 positive gives Zn2 positive plus Cu. Cell representation. Here we know that in the cell left hand side is anode, right hand side is cathode. So here anode reaction is Zn, that is Zn2 plus salt bridge Cu2 plus Cu, that is E0 cell equals to, we know that E0 cell equals to E0 right minus E0 left. Here E0 Cu2 positive Cu minus E0 Zn2 positive Zn. Putting the value, then E0 cell equals to 1.10 volt. According to Nernst equation, E cell equals to E0 cell minus 0.0591 by n log concentration of Zn2 positive into concentration of Cu by concentration of Cu2 positive into Zn. We know that the concentration of solid equals to 1, so Zn and Cu equals to 1. So putting the value of E0 cell, that is 1.10 minus 0.0591 by 2, here number of change of electron equals to 2, that is n equals to 2 log Zn2 positive by concentration of Cu2 positive. So equals to 1.10 minus 0.059 by 2 log 0.1 by 0.1, so cancel each other, equals to 0. So E0 cell equals to 1.10 volt. Question number 4. Calculate the del G0 and del S0 at 298 Kelvin for the fuel cell reaction, that is 2H2 plus O2 gives 2H2O. E0 cell equals to 1.23 volt. Del H0F for H2O equals to minus 285.8 kilojoule per mole. Answer. We know that del G0 equals to minus NF E0 cell. Here reaction equals to 2H2 gives 4H plus 4 electron. N equals to number of electron exchange equals to 4. F equals to Faraday, that is 96,500 coulomb. E0 cell equals to 1.23 volt. So del G0 equals to minus NF E0 cell, and putting the all value and gives minus 474.78 kilojoule. Also del G0 equals to del H minus T del S0. So del S equals to del H0 minus del G0 by T, putting the all value, and del S0 equals to minus 324.9 joule per Kelvin. I think you are enjoying to watch my video. I hope you are understanding all the points. If are not clear, so comment, I will be replied it. If are you need to discuss any topics, please comment me. I will be discussing for you, and stay with your chemistry lab. So thank you everyone. Bye bye.